Perfect. So today I would like to continue the story about self-adjoint operators. And let me start with some simple remarks that I didn't give you last time, and at the same time maybe I recall a little bit some of those definitions. So let me recall that an operator from D of A to H is symmetric if the following holds true. So you can pass it from one side to the other for all U and V in D of A. So let me prove a simple proposition. So let's assume that A is symmetric, and let's assume that it has an eigenvector with eigenvalue lambda. So of course we assume that the eigenvector is non-zero. So then, similar to the finite dimensional case, lambda has to be real. Here is a very short proof. Well, we write for this vector two sides of the definition. Here u is simply equal to v. Now, well, since it's an eigenvector, we have this equality, we replace AU by lambda u, and now we use the fact that the Hermitian product is antilinear in the first factor, and it is linear in the second, which now implies lambda minus lambda bar times the bracket, this is the product of u with itself, is 0. Since u is non-zero, so this is the square of the norm of u. It's non-zero, so lambda is equal to lambda bar. And we see that lambda is real. So this is exactly as in the finite dimensional case. We'll return maybe a couple of classes from now, we'll return more to these kind of considerations. But at the moment, that's fine. Now, another very simple proposition that we'll find useful later today. Suppose that A is again symmetric, and A is a non-vanishing real number. So then there is the following identity. So I form a new operator. I add to A an imaginary unit times the unit operator with a multiple A. And I take some vector u, and then the following simple but interesting identity holds true. So the norm square of this guy is equal to the norm square of AU plus the norm square of u with a coefficient a squared. Maybe one remark on notations and definitions. So by definition, we say that the domain of that guy, right, we just simply put it equal to the domain of A. So here, for all u in the domain of A. Also, another thing about notations, of course, it's more correct to write A plus plus this scalar times the identity, but we often, and many people, often abbreviate and don't write the identity. Right. Now again, a simple proof. So a plus IA u squared. So what is it by definition? It is this guy, right? It's a product of a plus I small a u with itself. Well, now we can simply write all the 4 terms which come out of it. And then what will it be? AU, IAU, right? So just opening the brackets, there are 4 terms. Well, the first term is one of the terms that we want. It's the norm square of AU. Now, with the second term, there is a square, there is an I, and there is a minus I. Their product is 1. And then there is a norm of u squared. So, so that's the second term that we want. Now, what happens with the other terms? So let me put here IA outside, and here I will have AU, U, and here there will be a minus sign because of the anti-linearity, so minus U, AU. Well, now since the operator is symmetric, this is simply 0, and so that's the answer that we want. So this is also a completely finite dimensional argument, so nothing changes. Very well. So is it enough of a Monday morning warm-up? One can go to something which is somewhat more infinite dimensional. So let me recall that actually the interesting part of the infinite dimensional theory is related to the fact that symmetric and self-adjoint, these are different notions. So let me recall the definition. So the domain of A star, these are elements of H such that the linear functional is bounded on D of A. And so A is self-adjoint. This means 2 things. A is symmetric, and this is usually a simple notion, but the second and important one is that the domain of A star is equal to the domain of A. So now this definition is good, but we probably need some more practical ways of deciding whether the operators are self-adjoint or not. And now I will formulate and prove an important theorem about it. And then maybe we go over a little bit of other criteria or other methods how we can establish whether the operators are actually self-adjoint or essentially self-adjoint. Now, an important theorem. So let's assume that A from D of A to H is symmetric. So then A is self-adjoint if and only if the image of the operator A plus I coincides with the image of the operator A minus I and is equal to H. Maybe before proving it, a small remark. So in fact, here it is not very important to have I and minus I. You can actually put here some multiple, A bigger than 0. Just you can put, like roughly speaking, any point on the positive imaginary axis and on the negative imaginary axis. So this doesn't matter so much. So this choice of I or minus I. You can see it basically because you can always, for instance, multiply your operator by a positive real number. So then it would scale the operator and it would automatically scale this I. Okay. Now proof. Why is it true? Maybe we start with that direction of the proof. So this, I think, in some way is easier. So let's assume that the image of A minus I is equal to H. Now let's choose some vector v in the domain of A star. Okay. So then let's apply A star minus I to v. Well, we obtain some vector of H. Since we obtain some vector of H, this means that you can find some vector u in the domain of A, such that this holds true, right? So this is some vector of H, but H is the whole image of A minus I, so there is a vector u such that this is true. But then let me recall from the last time that the domain of A, if A is symmetric, is always contained in the domain of A star, and on the domain of A and A star actually coincide. So this means that this is actually equal to A star minus I u. Well, so this implies that the vector u minus v is in the kernel of A star minus I. Right? Because, right, just simply because the image of A star minus IV is equal to the image of A star minus IU. But then, by one of the properties that we showed last time, so this is the same as the orthogonal of the image of A plus I, because that's the adjoint of A plus I. But then this is the same as H again, orthogonal. But H orthogonal is 0. There is nothing there, right? So this is 0. Or I should probably write it this way, but I just write it as 0. So this means V is equal to U, but U was in the domain of A. So an arbitrary vector of the domain of A star is in the domain of A. And this means d of a star is equal to d of a. Right. And together with the assumption that A is symmetric, this shows that A is actually self-adjoint. Well, now what about going in the other direction? So now we assume that A star is equal to A, right? This implies, of course, that A is symmetric. And this applies that the kernel of, let's say, A minus I, right? That's the set of eigenvectors with eigenvalue I. But we know that to have eigenvectors, the eigenvalue better be real, right? So there are no eigenvectors with eigenvalue I. So this is 0, right? So this means that so this means that the of course, A is equal to A star. Let me write it also this way. This is an identical rewriting it, but let me just denote it for a moment by A star. And this means that the orthogonal of the image of A plus I is 0. And in turn, this says that the image of A plus I inside H. So this doesn't need to be the whole of H, but it is dense because its orthogonal is 0. And I want to show that it is not only dense, but it is equal to H. Okay. Well, now since it is dense, then for any vector, let me see how I want to denote it. Yeah. So suppose I choose some vector in H, and since the image is dense, I can always organize a sequence of vectors A plus I un, which converges to that given vector. Now those UNs they are in D of A. Well, this sequence is converging. This means this is a Cauchy sequence, right? So it's a Cauchy sequence. And this means something like this. A plus I, un minus um, let's say squared, smaller than whatever epsilon squared, or epsilon as you want, for n, m large. Okay. Now let's use the small proposition that I proved before, right? So actually this thing, I can rewrite it as A un minus um squared plus un minus um squared. Well, that's kind of interesting, right? Because this tells us, so this sequence is Cauchy, but then there are two more Cauchy sequences. So we know that AUN is Cauchy, and the sequence UN itself is also Cauchy. Well, now Cauchy sequences converge in our complete Hilbert space. So this means AUN converges to something, let's call it V, and UN converges to something, let's call it U. Maybe I can erase this one. So now let me recall A star equal to A implies that A is a closed operator. Recall A star is always closed, so A is closed. Now, if you still remember from last time the definition of being closed, so this thing, right? So closed means the closed graph. Now we have a sequence of points in the graph UN, AUN, which converges to some point. So this means that that point, UV, is also in the graph. So in other words, what this means is that U is actually in the domain of A, and V is equal to the image of AU. Now, if this is the case, so then let's re-examine what our W is. So W is the limit of the sequence A plus I UN. But now we can compute this limit. So the limit of AUN is equal to V, which is AU, and the limit of UNs is U. Right? So this limit W is actually equal to A plus I U. And this guy is in the image of A plus I. So W is in the image of A plus I, and this means that the image of A plus I is equal to the whole of H. And then, of course, it's similar for the image of A minus I. Okay. So that's a powerful theorem that we're going to use today for various purposes. But now maybe let's just make a small list. It's not going to be a very, very long list, but still some kind of list of things that, so the ways how we can establish that an operator is self-adjoint or essentially self-adjoint. So let's say facts. Now, one fact, just to remind you, there is an exercise for later today, and I think maybe it was even a homework, right? Some kind of possibility to show that A is essentially self-adjoint. So we assume that we have an operator defined on some domain, and we assume that in this domain We have an infinite set of eigenvectors. We identified an infinite set of eigenvectors with real eigenvalues. And we assume that this set is a Hilbert basis of H. So inside D of A, we found a basis of eigenvectors with real eigenvalues. So then A is essentially self-adjoint. So this means that you can relatively easily correct the domain. You can, if needed, make the domain a little bit bigger, and then A will be self-adjoint on that domain. And that you can do in a unique way. So there is a unique self-adjoint extension. So another interesting fact, you can actually weaken the conditions on this side. So A is essentially self-adjoint if and only if the image of A minus I closure is equal to the image of A plus I closure and is equal to H.
So maybe in the first statement, I think what you mean is really that you have a Hilbert basis of H.
Yeah, the Hilbert. Yeah, sure. But we never worked with actual basis. That's why I was a bit hesitant. You know the difference between the Hilbert basis and the basis? So the Hilbert basis, that's what we were always discussing. A basis of a vector space a priori, that's a set of vectors such that every vector admits a finite decomposition, right, in terms of those vectors. So we never deal with this notion. That's why I didn't want to bother you by reminding you what it was. But okay, that's certainly, whenever we say basis, we always mean a Hilbert basis. All right. Now, one more thing. In fact, this topic is a kind of theorem. We're not going to prove it here. Part of the proof is outsourced for the next problem set, but we're going to give an example. So let's introduce the following notions. So let me introduce two numbers, n plus of A is equal to the dimension of the image of A plus I orthogonal, right? So that's a closed subspace. It has a dimension, possibly infinite. So recall that this is the same as the dimension of the kernel of A star minus I. And n minus of A is equal, similarly, dimension of the image A minus I orthogonal. And this is the dimension of the kernel of A star plus I. So these are called the deficiency indices. So these are numbers, possibly infinite. So theorem. Let's say A from D of A to H is symmetric and closed. So then it admits self-adjoint extensions. So let me recall, so B is an extension if the domain of B contains the domain of A, and on the domain of A and B are the same, right? So this is an extension, and this extension is self-adjoint. So there are such extensions. If and only if the deficiency indices, so the dimensions of those interesting looking subspaces, they are the same. Now, moreover, there is a complete classification of those extensions. Actually, B is not unique. Now, maybe there are many B's which are self-adjoint. So, so those B's, the self-adjoint extensions of A, are in one-to-one correspondence with operators U, which map, let me decide what they map where. Let's say they map the kernel of A star minus I to the kernel of A star plus I. Now, these are the subspaces of the same dimension, and we require U to be unitary. So it preserves the Hermitian product. So this space has a restriction of the Hermitian product of H, that space as well, and so the map should preserve the Hermitian product. So maybe I should write it. So U of U, U of V is equal to UV. Right. So then, suppose we are given such an operator U. So what will be the domain of B? I will denote it by BU. So that's the self-adjoint extension corresponding to U. So it consists of vectors of the following form: U naught plus U plus plus U minus. So U naught is in the domain of A. U plus, let me denote this space by V plus and that space by V minus. So U plus is in V plus, U minus is in V minus, and U minus is the image of U plus under that unitary operator. Right? So in fact, I need to give you U naught and U plus, then U minus is defined automatically. Right? So you see the domain is bigger than D of A. You add those vectors U plus plus U minus, where U plus and U minus are related by the unitary. And how does BU act on U naught plus U plus plus U minus? That's actually also quite interesting. Of course, on U naught, it acts by A because it has to be an extension, right? On the vectors of D of A, it has to act like that. And then it multiplies U plus by I, and it multiplies U minus by minus I. So you see that these are kind of really beautiful and interesting. As I say, we're not going to prove that theorem, but part of it, the fact that BU is symmetric, you're going to prove in the next problem set on Wednesday. Instead, we'll now work on an example. So let's see how it works in practice. So that's another way of creating self-adjoint operators. All right, so an example. Well, my usual example is A is an operator minus I d over dx. Now, of course, the question is, what's the domain? Let me choose the domain that we were already considering once at last time. So I take u to be continuously differentiable functions on 0, 1, and I impose those unreasonable boundary conditions, right? So could you recall me what we've seen about that operator, right? So that operator is not very good. Why is it not very, or whatever, in which way it is not very good? So it's symmetric, right? But it's not, for sure it's not self-adjoint, it's even not essentially self-adjoint, right? So symmetric. But it's not essentially self-adjoint. I must say that to really use that theorem, our operator needs to be closed. I don't think this operator is closed, but we'll be working with it anyways. So let's consider the following. So recall that we've shown last time that the whole C1 of 0, 1 is contained in the domain of A star, right? So here, in principle, to define V plus and V minus, we should be using the whole domain of A star. But again, let's ignore this fact. So this thing is already a huge part of the domain of A star. Let's try to solve those eigenvector equations for A star. So we want to find eigenvectors of A star with eigenvalues plus and minus I. So let me recall that A star, on that domain, we've shown it actually given by the same formula, right? So A and A star are given by the same formulas, but the domains are different, right? So V plus, we want to solve this equation minus I du over dx is equal to minus I u, right? Is it correct? Yes. Plus, sorry. Okay, so what are solutions of those equations? So solutions of those equations are constant times exponential minus x, right? Now what about V minus? So we are now solving the equation minus du over dx. This time, hopefully, we get a minus sign. And so this would be c times the exponential of x. But if you don't mind, I will write it in the following way. I will write it as the exponential of x minus 1. Of course, this doesn't matter, right? Because it's just the renormalization of this c. What does the wisdom of this theorem say? So, okay, I have my V plus, which is in this case, at least within this domain. So this V plus is one-dimensional right? It's c times this function. And v minus is also one-dimensional. It is c times that function. Now, why did I choose them in that way? That's because the L2 norm of these two guys is the same. Is it right? So note that the L2 norm of this guy is equal to the L2 norm on 0, 1 of that guy. Right? That's why I kind of subtracted 1. So I should choose a unitary operator acting from one-dimensional space to the other one. So they're equipped with bases. They are not normalized, but at least they have equal norm. So an operator u should be sending e to the power minus x to e to the power x minus 1 times possibly some number z of absolute value equal to 1. So z is equal to some exponential of an angle, right? Okay, very well. So now let's try to implement it in practice. So now we have the domain of bu. What will it be? Well, u of x will be equal to u naught of x plus I choose an arbitrary vector in v plus. An arbitrary vector in v plus is c times exponential minus x, right? Plus I should take z times c times exponential of x minus 1. And this is for all u now in, let me denote this guy, c1 u naught, c1 0 1 u naught of 0 is equal u naught of 1 is 0. And c is an arbitrary complex number, right? So that's how it looks like. Now maybe let me write it here. Where bu maps this vector, it maps it to minus I du naught over dx plus I c exponential minus x, right? Minus I z c exponential of x minus 1. But notice that actually this action, that's again minus I d over dx. Right now, concretely, this vector is exponential minus x. If we apply minus I d over dx, we get plus I here. If we apply minus I d over dx to that guy, we get minus I this. So the operator bu is always, for any u, is minus I d over dx. Just the domain changes. So, what is this change of the domain? So let me give you two examples. So let's choose phi equal to 0. So what happens? So actually, the only thing that will change, these are boundary conditions. So if we are interested in the expressions for u of 0 and u of 1, u naught does not contribute because it's actually equal to 0 at both endpoints. So this is what? This is c e to the power minus x is 1, right? Plus z is now equal to 1, c times e minus 1, right? That's the value of the second function. Now what we get at the other endpoint? Well, it will be c to e minus 1 plus c. So now that they're actually equal to each other, right? So this is actually periodic boundary conditions. And if I'm not mistaken, later today at the exercises, we will be looking at this operator with periodic boundary conditions, and we'll be showing that it's actually essentially self-adjoint, right? So that's what we have. Now, what about, for instance, phi is equal to pi, right? Z is equal to -1. Well, u of 0 will be c minus c e minus 1, and u of 1 will be c e minus 1 minus c. So what is this as boundary conditions? So what's the relation between u of 0 and u of 1? Right? These are anti-periodic. Yeah, so this is u of 0 equal to minus u of 1. And well, I let you meditate on what happens for other phi's. So that's an interesting instrument. So that's called the Friedrich's theory of self-adjoint extensions, and we'll see some further examples of it. Sorry for being somewhat over time. Let's have a break, and we continue the story after the break. All right, so let's continue. I would like to show you one more fundamental result about self-adjoint operators, and then we'll dive more into examples. So maybe let me start with a remark. So remember, in the finite dimensional setup, self-adjoint operators, these were our observables. And observables, they formed a vector space, right? You could have added two observables, and then you would get, so dimension, either dimension is finite. So A self-adjoint and B self-adjoint. So this means that you can form a sum or some other linear combination, and this will be a new observable, a new self-adjoint operator. Well, if the dimension of H is infinite, well, this doesn't quite work so easily. That's because all those operators a priori, they have domains. So A plus B is naturally defined on the intersection of the domains. But the intersection of the domains may be not dense, or maybe just zero, right? So all kinds of things may happen with the intersections of the domains. So actually, so in fact, if A is unbounded by if B is bounded, it still works very well. And there is an exercise in the next problem set about it. But I will now show you a theorem. So it goes under the name of Kato-Rehlich. And this theorem tells us, it gives us one particular useful situation when you can add two unbounded self-adjoint operators and obtain a new self-adjoint operator. So here is the setup. We have A, an a priori unbounded operator, self-adjoint. So we have another operator, also self-adjoint. And we have the following conditions. So first of all, we assume that the domain of A is contained in the domain of B. Already that. And we also assume that we have the following estimate. So this is for all u in the common domain, which is the domain of A. And importantly, we assume that so these are of course positive coefficients, alpha and beta. And we assume that alpha is strictly smaller than 1. So the operator A plus B, it is naturally defined as an operator on D of A, right? Because D of A is also in the domain of B. Is self-adjoint. So you see, actually one has to be, so this is one specific result, but already you imagine there are no general schemes. So that's one possible scheme how you can build operators by sums. And we'll see later today, even I think during this hour, that in quantum mechanics we do want to do things like that. So that's something that you're doing all the time. So, well, you better have this mechanism. Now proof. So we know that for all A, let's say in R positive, we have image of A plus IA equal to image of I minus IA equal to H, right? So that's by the criterion that we proved at the previous hour, right? So we can choose any A and we have this. Now, there is one problem in the next problem set, so I don't want to spend time here on proving these things, but it's a relatively easy exercise. First of all, those operators, they admit inverses, and those inverses are bounded. So these are bounded operators, and there is a following. So there is a following bound on the operator norms, and also those operators, even if you multiply them by this a priori unbounded operator A, so this operator is still bounded. And there is a bound on the norm which is now equal to 1. So these things we admit, but then you prove them. Okay. So now what do we plan to do? So let's consider the operator A plus B plus IA. So this is a well-defined operator, right? And let me rewrite it in the following way. 1 plus B times A plus IA inverse plus IA inverse times I plus IA, right? That's just an identity. Now let me show that this operator is actually bounded, and let me estimate its norm. So I'm looking at the operator dA plus IA inverse times some vector u, and I'm using this bound. So it's smaller than alpha A plus IA minus 1 u plus beta I plus IA minus 1 u. Now this first operator we decided is bounded, and its norm is bounded by 1. So actually this expression I can estimate by alpha u. Well, this expression I can also estimate because this operator is also bounded, and its norm is bounded by a minus 1. So you see this operator is bounded, and its norm has this estimate, alpha plus beta over A. Now, let's choose A. Right? A was something that we chose ourselves, right? So let's choose it in such a way that alpha over beta divided by A be smaller than 1. Right? Alpha was smaller than 1. Beta is some fixed constant. Let's choose A so large that alpha plus beta over A is still smaller than 1. Right? So if this is the case, then the norm of beta plus IA inverse is strictly smaller than 1. So we have now an operator C, which is B times A plus IA minus 1, and the norm of C is strictly smaller than 1. So then I claim that the operator 1 plus C is invertible with bounded inverse, which is simply given by 1 minus C plus C squared minus C cubed plus so on. So, you know, it's just like a function in one variable, or like if it were a finite dimensional matrix, right? You just take this series, you see that it converges in the operator norm, and then the operator to which it converges is the inverse of 1 plus C, because if you multiply 1 plus C by the series, you get 1, right? So this is just as in the first year calculus or in the finite dimensional matrix algebra. So there is no difference, right? So the series converges in operator norm. So this means this operator is invertible, right? Now, this implies that the image of A plus B plus IA, well, this is an invertible operator, so the image of this guy is equal to the image of that guy, right? And the image of that guy is equal to H, right? Because A is self-adjoint. And of course, there is a similar argument with a different sign, right? We never really used what was the sign, so we can actually add the second sign. But then by the criterion we proved before, right, the image of these guys, they're equal to H. This means that the operator is self-adjoint. Right. Okay. So much of abstract stuff. Now I would like to spend the rest of this class. First, we're gonna dive a little bit into the operators, into the zoo of operators that we actually want to use in quantum mechanics, and then we're gonna apply the Kato-Relix theorem to some particular situation which is relevant in quantum mechanics. Okay, so something about operators which are popular in quantum mechanics. So one thing which is, first of all, which is very popular, we can take H to be L2 of Rn. So then let's say we take a function on Rn, and let's say so this is rather general. We take an arbitrary measurable function. So then we can define an operator. Let's call it V hat, sending an L2 function to V times this L2 function. And of course, we should say what is the domain. So one particular case is considered in the exercises, but like a general case is as follows. You consider L2 functions, and you require that. So this is a real valued. So we require that the integral of v squared times absolute value of u squared converges, right? So we require that the resulting vector be also in L2. Over Rn, yeah. Okay. So those operators are self-adjoint. So as I say, So there is an example of this phenomenon in problem set 6. In particular, of course, important operators, they correspond to V that you simply choose equal to one of the coordinate functions. So these are operators which or of course any other function of x. So to introduce other examples, let me recall the following facts about the Fourier transform. Well, let me call it U tilde, U to U tilde. Well, there are many ways, right? There are many theories of the Fourier transform. One possible theory, which is probably good for us, is through the Schwartz functions. Let's introduce the set of Schwartz class functions. So these are C infinity functions on Rn, such that the supremum over x, I'll now introduce those notations. So the suprema of all such expressions are finite, and here x to the power I, this means x1, I1, xn, in, and dj means d over dj1 over dx1, j1, and so on, djn over dxn, jn. So any polynomial times any derivative of u, so all the suprema like that are finite. So this means that actually u's, they have to decrease pretty fast, faster than any one of a polynomial at all kinds of infinities. So that's roughly the in particular. This implies, among other things, so the conditions on S are very strong. In particular, this implies that the functions of that class are integrable and square integrable on Rn. So now we introduce the Fourier transform by the standard formula. So integral over Rn. And here Kn, Kx is simply the standard scalar product. So the fact or facts are as follows. So F defines a bijection on S. So it maps S into S bijectively. And the following identity for the L2 norms holds true. And then as a consequence, admits a unique continuous extension to L2 of Rn. So now instead of S, we take L2, and we still have a bijection which satisfies this property to unique unitary extension. So maybe just one word, why do we have to talk about S? So that's because a priori for an element of L2, this expression does not make sense, right? So if you say U is in L2, then this thing would make sense if this guy were also in L2. But this guy is manifestly not in L2, right? Its norm is clearly infinite. So just if you say that this formula defines the Fourier transform in L2, it does not make sense. However, S is dense in L2, and you extend this formula from S to L2 by continuity. So this does make sense. Okay. So now, why do I speak about it? Because on S, F has a very nice property that probably all of you know very well. So if you apply the standard operator of the type minus I, the partial derivative in xj to u, then the result will be a multiplication by kj of the Fourier transform. So now we can define, similar to what we've done here, we can define many new interesting operators. So let's say we have W an R-valued measurable function of k's. Now we can define W hat with the domain so these are elements of L2 such that what? Such that the integral over Rn of W squared times U tilde of k squared dnk be smaller than infinity, right? So it's again defined as some kind of multiplication operator. Now where does W hat send U? Well, first of all, we apply the Fourier transform. So then we multiply by W, and then we Fourier transform back. So, right, so that's just exactly the same construction as we used before, but now we're using it after this Fourier transform. So this defines for us a new family of operators, and maybe one should give examples of those operators. Of course, the so-called momentum operators, which correspond to W equal to some kj. And we see that on an appropriately chosen domain, right? We can also identify them with minus ID over dxj. But of course, so this would hold on part of the domain. So that's the real definition. Or, as we were doing up to now, we were taking minus ID over dx on some smaller domain and then saying that it admits a unique self-adjoint extension, right? So there are two ways to do that. Either to describe the domain explicitly using Fourier transform, or define those operators on some smaller domain and then do the self-adjoint extension. Or we can do the operator, we can choose W equal to sum over I ki squared. And this corresponds to the self-adjoint extension of the operator minus Laplacian, so minus d2 over dx1 square minus d2 over dx n square. So these are one should say that kind of usually when we speak about this stuff, we prefer to refer to those operators. We maybe sometimes omit those words, so that this guy is defined on some sufficiently small domain and then we take a self-adjoint extension, or that we can go to the Fourier transform and then define precisely that domain. So usually in the common speak, we would say just minus Laplacian or minus I d over dxj. But that's how it actually works. All right, so let me end this class with the following interesting theorem. Okay. So now suppose that H is equal to L2 of R3. We're kind of interested in R3, right? So that's one of the interesting examples. And let's assume that the potential function is a sum of two pieces. So one of those pieces will be a square integrable function. And the other piece will be a bounded function. So the infinity norm, right, that's the absolute value norm. So this is so this means it's bounded. So then the operator A equal to minus Laplacian plus the multiplication operator by this potential V is self-adjoint on the domain of minus delta. So you see that's probably one of the most popular operators in quantum mechanics. So this is so-called up to multiple, so-called kinetic energy. This is a potential energy. That's right what you usually take for a Hamiltonian in your quantum mechanics. So this is the one of the main sources of Hamiltonians. Now we are interested in the question when such things are self-adjoint. And here is one possible answer. As you see, kind of it's rather specific. So so there is this R3, there are those kind of funny conditions. So probably not at this class. Next class I will show you more examples and counterexamples of when things are self-adjoint and when things are not self-adjoint. But for now, let's prove this theorem. So this should be an instance of Kater-Rehlich. So proof. So the general strategy is to use Kater-Rehlich. So we need to show some kind of Kater-Rehlich type estimate for minus delta and for V. So let me start with the following equations. So let me consider U in C infinity of Rn and maybe compactly supported. Maybe later on I'll change my mind and say that it's simply equal to, that it may also be in S in this Schwarz class. Clearly it is in the intersection. It is in the intersection of the domains. And it is clearly dense in both domains. Now, let me introduce one more function. Let me call it chi of k. And this will be, what do I want it to be? 1 plus k1 square plus so on kn square to the power minus 1. A small remark. So chi is an element of, is a square integrable, right? So here it is 1 over k square, the behavior at infinity. Now the behavior of the square is 1 over k to the 4th, and this integral in 3 dimensions, it has k square dk, right? So this is like dk over k square. So this concrete function is square integrable on R3. Okay. Now let's do a little bit of functional analysis. So let me look at the infinity norm of my element U. So what's the infinity norm? Well, whatever. You see I'm preparing some Fourier transform. That's why I multiply by this funny factor. So that's the supremum of R3 of the absolute value of U of x, right? I can now rewrite it using the inverse Fourier transform. So this is supremum over x in R3. And here that's the integral exponential ikx u tilde of k d3k, right? So that's using inverse Fourier. Okay. Now let's estimate this guy. So that's estimated by the one norm of U tilde, right? Which is equal to the which is equal to the integral of U tilde k d3k over R3, right? Now let's do the following. So let me write here chi of k and let me write here U tilde k divided by chi of k d3k. Right? Now it looks like a Hermitian product in L2. Right? This guy is actually real valued. So if I want, I can put a complex conjugate on it. It doesn't change anything, right? So it's a Hermitian product in L2 of those two things. So I can estimate it by Cauchy-Schwarz. So this is estimated as an L2 norm of chi, which is finite, times the L2 norm of this guy. So let's have a look. Let's have a look. What is it? So the L2 norm of that guy is 1 over chi squared, which is is it what I want? Yeah, that's always like this with this functional analysis. 1 over chi squared. Well, one over chi squared. Yeah, right. Right. Right, that's right. Right, that's the expression, right? Now let me recall. So what is this thing, right? So it looks like a norm of some vector. And what is that vector? It's U tilde of k times 1 plus k squared, right? So let me rewrite it in the following way. So this is the norm of chi, and here let me write it in the following way. This is minus delta plus 1 acting on u squared. Right here, minus delta, so that's that self-adjoint extension of the Laplacian. Remember that this corresponds to k squared. 1 corresponds to 1. So here it's written in the Fourier transform. Here it's written just in this other notation. So now one more estimate. It is chi-square, and here minus delta u squared plus u squared. Is it really true? Sorry, today, like towards the end, it is kind of, no, sorry. No, yeah, right. No square, and then all of a sudden the triangle inequality helps us. Right. Of course, with squares, I'm always kind of trying to write some wrong formulas, but the formulas, they want to correct themselves. All right. So now, this is supposed to be some kind of Carter-Ehrlich estimate. But actually, it's not, right? Because this coefficient has to be smaller than 1. We don't know what it is. We probably need to compute it. Maybe it's not smaller than 1. Probably not. Now, then we do the following interesting step. So that's the last step in the proof. It's a scaling transformation. So let's introduce a new function, u tilde lambda of k, which is equal to lambda cube u tilde of lambda k. So I rescale the argument, and I rescale the function. I think it's easy to check that this corresponds to u lambda of x equal to u of lambda minus 1x, if I'm not mistaken. So I have to rescale the arguments, and at some point I should also rescale the functions. All right. So now notice the following. When you do the one norm, right? When you do the one norm, if you do such a rescaling in the one norm, so then this lambda cube would exactly compensate the change of variables for k to lambda k. So if you do this, so the one norm does not change. So starting from this point, we can deviate in our argument and say u tilde 1 is equal to u lambda tilde 1. Okay. Okay, that's very good. Now, now this would give us then the arguments would go through, and we'll now have this estimate, but we should have a look at what happens to those guys. And if you, so let's denote this guy by C, and if you make the substitutions, we'll find out that the behavior will be like this: lambda minus 1/2 minus delta u plus lambda to the power 3/2 u. So if you go through the scaling, you will see that these two terms will scale differently. Now, see, that's the interesting situation. You can choose lambda. Lambda is an arbitrary positive number. So let's choose c over lambda 1/2 smaller than 1. and call it alpha. So this is equal to alpha minus delta u plus beta u. So this is smaller than 1. And that's the Carter-Rayleigh estimate. So unfortunately now we don't have time to discuss the consequences, but so next time we'll discuss examples and counterexamples, and also finally go into the spectral theorem for unbounded self-adjoint operators. That's what's going to happen Wednesday. Okay, well, I think that's it for today. Thanks.